Now the arrow diagram is great for saying which subshell to go to next, and it's according to the lowest n plus L rule. But atoms don't know this rule. And I'll tell you why, but not why atoms don't know this rule, but there are exceptions to this. And basically, it doesn't fill a subshell. I'll show you what I mean. The first exception occurs with chromium, the element chromium, which is atomic number 24. Okay? So the 24 electrons around a chromium atom, we would expect to do this, okay, according to our arrow diagram. Chromium is a D block element. Hopefully this is kind of coming back to you. Remember, D block means that's kind of where the last electrons are added. If you kind of use the periodic table, you know it's 3D because it's in period 4. And you know it's 3D4 because you skip over 4 elements. Chromium, it's just a beautiful system. 1, 2, 3, 4. That's why it's 3D4. Okay? But what it really does is this. Okay? Now, if you're like me, you have to kind of blink. You're like, I don't see a difference there. But if you look closely, oh, no, this is what it does. You're like, I don't see a difference there. So this is the actual down here. So notice that instead of having the 2 electrons here in the 1s, it has 1 electron. Excuse me, 2 electrons there in the 4s. It has 1 electron in the 4s. And instead of having 4 electrons in the 3d, it has 5 electrons in the 3d. So it kind of, 1 electron that was tucked away in the 4s kind of jumps ship, okay, and is promoted to the 3D. And there's a reason for that. It's just not random. So if I were going to put boxes down here for a D-type subshell, how many boxes would I put? 1, 2, 3, that's a P, 4, 5. Yep. That's any D, including 3D. Yep. So the whole 5 is kind of a beautiful, we talked about Fairfield, it's kind of a beautiful resonating sort of number, okay, when it comes to subshells that have 5 orbitals. Okay. So how many orbitals for an S-type? 2 electrons and 1 orbital. Yep. Yep, 1 orbital. So in this situation down here, the 4s is half filled and the 3d is half filled. So that's kind of why that happens. So the example we saw with chromium was that 1 lower electron jumped up to a D type. The S jumped up to a D type. Sometimes we'll actually see an S jump up to a D type and totally fill the subshell. And of course, Fs have 7 boxes, 7 orbitals. Okay, and so sometimes there'll be some jumping around to get a half-filled subshell of F-type subshell or a full F-type subshell. So I'm hoping you guys would already figure this. So 24 protons, atomic number 24, that's chromium. You don't have to memorize this list. Another exception occurs in the same period. It's atomic number 29, so it's copper. Okay, copper is an exception to the lowest n plus L rule. Then in period 5, you see there's several elements that don't follow the rules. So with all of that said, though, on your unit exam, you're going to want to follow the rules. Okay, I won't give you any on purpose that are exceptions. I think I can handle that. So you will always follow the rules, but I just need to tell you why they don't follow the rules. Okay. So then the other thing we need to cover is this thing about valence electrons. So Monday we talked about that as we were kind of jumping and skipping and coming up with how electrons are configured. We said that if you come up with 6 electrons in a p-type subshell, NP6, where n is the energy level, so okay, starting with n is equal to 2, they've all got them. Then you've reached a rare gas, okay? And we said that if you take 2 plus 6, you of course get 8. Okay, so that's your famous octet. And that's leading up to a rule that we're going to be using for atoms to form ions and for atoms to share electrons in covalent bonding because they want to get a complete octet. All right. So as we are coming up with how electrons are configured, we actually on Monday said we can use our arrow diagram and kind of come up with the list of subshells, and we'll superscript mean how many electrons, and that's in the order of filling. And sometimes it's helpful to kind of unscramble it in the order of increasing n. It's the same electron configuration, but you put the highest n at the end. Yep. And you don't have to do that, though.
So that's just,
Yeah, no, that's totally optional. In fact, if I was doing it on a test, I wouldn't unscramble them. But unscramble them has its advantages. It actually kind of highlights the highest n, and those electrons are your valence electrons. And they're the most important. So for potassium, what we did the other day, I think there's 40 electrons around a potassium atom. Oh no, that's zirconium. Potassium, there's only 19 electrons. There's 19 electrons here. This is in order of increasing n. This is kind of already unscrambled. So how many and where are the valence electrons here?
they would be in the 5s2.
Right,
So
5s2.
it'd be 2 electrons.
Yep. Now, if you find potassium, that's not right.
Is it 19?
Yeah. That's good.
This is strontium. What is going on here? My slides? Let's add up. That's not 19.
that'd be 2.
How many electrons do we got there? Quick. Okay, so that's neon. That's 10. That's 18. 28. Yeah. 30. 40. 40 electrons.
So that'd be,
Zirconium. Yeah, that is zirconium. Final answer. That looked familiar. I said 40. Okay. So that's zirconium. 40 electrons. Sorry about that. Okay, so zirconium. What block is zirconium in? What sort of element is it?
it's like a D block.
It is D as in dog, exactly. So if we were in the order of filling, we're actually going to peter out with these, where did I see them? These electrons right here is where we kind of peter out. But what we're talking about is the highest n, and you told me 2 electrons in the 5s. Okay. All right, so is this really for iodine then? Yeah, that looks for iodine. I can tell because it peters out in this case with 5 electrons in the 5p. Iodine is a block P, which is awesome, and it's actually in the 5th period, so that's all consistent. So how many valence electrons here? What do you think? What's our highest n? N, the principal energy, the number 1. 5, yep. 5 is our highest, yep. So how many electrons there?
7.
Yep, 7. 7 valence electrons. Must be on my next slide. Yep, all right. But just for kicks, what group number is iodine in? It's a halogen in,
4p?
no, the group number at the top of the column.
Oh, 7a.
7A, yep. Yep, 7A. So actually what the next slide says is the group number actually is the number of valence electrons around that atom for the main group elements. Now, zirconium a little bit ago we said had 2 valence electrons. If it's following the lowest n plus L rule, actually all of the D block have 2 valence electrons. And all the F block also have 2 valence electrons. So this is periodic table. Now this isn't necessarily, anyway, I'm not going to add to that. I'm getting ahead of
The
myself.
slide before, there were 2 blanks I didn't quite catch, I'm sorry.
This one?
No, I think it was the next one.
Yeah.
Okay.
Now we've finished part 2. Okay. And then, of course, these were due today. All right. Now on to part 4. I've learned to be patient, sort of. Comes back. Right. Okay. So, let's see, do you have a, no you don't, compound, so we're on to part 4,
So we're skipping.
skipping part 3 for now, yep. And actually, the next slide that I brought in that you don't have is just to kind of remind you in the hierarchy of matter, like matter classification, where compounds are. So all matter has mass and occupies space. It's made up of atoms. Okay. We have pure substances, and we have mixtures. And there's 2 types of mixtures. There's homogeneous and heterogeneous. But with regard to pure substances, we have elements and we have compounds. CPD for compounds. And we can go back and forth between the 2 by some sort of chemical reaction. CHM165. Okay, so compounds, we'd use formulas to represent them and all that. We're going to dive more into the different types of compounds. 2 main types of compounds. This doesn't work, sorry. So I can take compounds and I can break it out into molecular and ionic compounds. We use formulas for both, and there's some things in common, but molecular CPD and ionic CPD. And it's really helpful in physical science, it's really helpful in chemistry to recognize the distinction between the 2 types of compounds. So actually, I'm going to go ahead and start a list here, a little tally. Molecular CPD here, and then ionic CPD here. All right. So first off, well, we use formulas to, like the formula for water is H2O. We use chemical formulas to represent both types of compounds. But if we have a repeating unit of a molecular compound, we call that a molecule, the name of it, the repeating unit. And if we have a repeating unit of an ionic compound, that's actually called a formula unit. That's the name of the repeating unit. Okay, so that's one distinction. Now here's another one, and in my intro class, I don't do it for you guys. You'll just have to kind of catch up as we go. But if you're just eyeballing the formula for a compound and you want to know which it is, molecular compound or ionic compound, you'll look for the metal. And so basically this says metals bonded with nonmetals form ionic compounds. So this is metal, I'll just put metal and nonmetal. And that's my chemical bond. Okay? Molecular compounds are not nonmetals bonded together. 2 nonmetals bonded together. So I tell students, if you have a metal, then by golly, in the formula, by golly, it's most likely an ionic compound. So we'll look for the metal. And we talked about the JAG. Remember the JAG on the periodic table goes like this is boron, okay, over in the P block. That's just terrible. But here we have metals and here we have nonmetals. Okay? So if we look for the metal, oh, by the way, hydrogen. We have hydrogen in a lot of compounds. Hydrogen, for purposes of identifying the compound as molecular or ionic, hydrogen is nonmetal, usually. Okay? So hydrogen, nonmetal, carbon, nonmetal, oxygen, nonmetal, nitrogen, nonmetal. These are all examples of molecular compounds. The synonym for molecular compound is covalent. Covalent compounds, molecular compounds, they're the same thing. Okay, what else do we need to know? So hydrazine, nitrogen, nonmetal. Nitrogen's a nonmetal. Hydrogen, for purposes of identifying as a molecular or ionic compound, is also nonmetal, so it must be a molecular compound. Ammonia, okay. So table salt, you guys would probably tell me the formula for table salt is NaCl, right? So, I almost said nitrogen. Sodium, Na, is over here, so clearly it's a metal, okay, so this thing's an ionic compound. And if this animation were to work, it would look something like this. I found my thing, or I found one of them. Okay, metals, one of the things they love to do is they give up an electron. So there's an electron transfer. Here's my little electron being transferred from the metal to the nonmetal. Okay. And in doing so, when that chlorine atom gets that electron, guess what? It becomes negatively charged. And when that sodium loses that electron, it becomes positively charged. And then we have a dot, 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 and that is a type of chemical bond that is an ionic bond. So I'm actually going to add something over here under ionic compounds. What I just described, that's an electron transfer. Electron transfer. So under ionic compound, I'm going to put electron transfer from metal to the nonmetal.
No, covalent, they're the strongest type of bonds.
No, actually, no. I think ionic bonds are stronger, yep. Electron transfer. From the metal, yep, to the nonmetal. And that leaves your metal negatively charged, makes your metal positively charged and your nonmetal negatively charged. And this is an ionic bond. I always think of James Bond. It has nothing to do with anything.
Can I ask a question? I don't know if I'm just stating the obvious, but it's like, because it's the electron that's negative, that's why when it goes over to the other part,
Yes.
it's the negative, and that's why
It leaves it deficient, electron deficient, it's
Leaves it
positively
positive.
charged. Yep.
Okay.
Now that's exactly how it works. One more thing, and if this would work, it would I don't see this like kind of square looking thing over here, kind of like a cube. A cool thing with ionic compounds is that they form crystalline lattice structures. And I know this is probably getting too low if I put this down here. Okay, they form in their solid state crystalline, and that's why they have very high melting points. They're very strong. Crystalline lattice structures. They're beautiful. So there is sodium chloride, table salt. If you were to look at it close up, it has these kind of nice facets. Kind of looks like you should put it in a ring, right? There's a field of science called crystallography, and it looks at solids. It looks at materials in their solid state, and it looks for these sort of repeating units. So I just think that is so cool. Yep. Before I move on, let me kind of show you how cool a crystalline lattice structure is. Do you buy this? Because we're going to talk about sizes of cations, sizes of positively, something that's picked up an electron. Do you buy this, that it's big? It picked up an electron. It's kind of like swollen. So over here, just glancing at it, I know that those yellow orbs represent the chlorine that's picked up an electron. And you actually kind of see, so these are our Cl minuses. This is our Na plus, it's smaller. Do you notice where it alternates? And it's got this whole kind of interconnectedness forming the crystalline lattice structure. Okay, so leaving crystalline lattice structures, back to molecular compounds. So water, oxygen, clearly a nonmetal, okay? Hydrogen, for purposes of identifying as a molecular compound, nonmetal. Okay, so it's a water molecule. So the cool thing about water molecules, unlike the sodium crystalline lattice structure we saw before, they are isolated. So if you can kind of pin down a water molecule, what this is trying to say is that oxygen has possession of those two hydrogens. It's like a little trio. Okay, they're not sharing it with anybody else. Okay, if we compare a water molecule to your sodium chloride crystalline lattice structures with the alternating Cl minuses and Na plus, it's kind of hard to see where one starts and the other ends. Actually, if you were to hone in for that particular crystalline lattice structure on any ion, it actually has 6 buddies. It's connected to 6 other things. Okay, so it's more of a community than a close-knit family. Okay, so I kind of talked you through this over here. Electron being transferred, the whole metal to the nonmetal. Okay. Now, over here, though, with regard to molecular compounds, I'm going to say in a molecular compound, I'll say all bonds are covalent bonds. I'm going to say covalent chemical bonds. And then I'm going to go ahead and say, with that, all bonds are covalent chemical bonds. And I'm going to say E for electrons shared. Electrons are shared. That is in direct contrast to this electrons are transferred here. So we kind of have, that's the yin to that yang. Okay, and we'll be talking more when we draw Lewis structures a week from Thursday. Oh, 2 weeks from Thursday, because we've got to get Thanksgiving in there. On the 1st, we're going to look at drawing molecules and seeing how electrons are shared. I'll go ahead and tell you why. You probably already know why. Why do they share electrons? To get a complete octet. That's it. To get octet. Oh my gosh, does that almost rhyme? Not really. To get octet. Okay. And like I said, in contrast to a covalent bond, we have the ionic bond, where electrons are transferred. Which direction are they transferred? It's like I said just a minute ago. It's always electrons are transferred, electron or trons are transferred from the metal to the nonmetal. And it leaves the metal, like Rhonda was saying, electron deficient, so it's positively charged. It leaves the nonmetal electron rich, so it becomes negatively charged. That's it. Let's see. Well, I guess I should add one more thing up here. Where I said E transferred, I'm going to go ahead and call that ionic bond. Okay. So, I don't know where to add this. But ionic compounds contain at least one ionic bond. I kind of think of an ionic bond in a series of atoms joined together where electrons were transferred just somewhere. It kind of contaminates the whole unit, and it makes it an ionic compound. So ionic compounds contain at least one ionic bond. The problem is, or the reality is, there are a lot of repeating units out there that kind of have a mixed bag. They have both electrons are shared and somewhere electron was transferred. Electron transferred, it contaminates it. It's an ionic compound. Covalent compounds, and I think I wrote here, covalent compounds, all bonds are covalent chemical bonds. I already wrote that down here. Very good. Okay. Electronegativity. Anybody know how is your Greek? So what's that the Greek letter for? That X-looking thing? No? I wouldn't know if I... No? Okay.
No?
It's the Greek letter chi. C-H-I. Like chia pet, but no, it's chi, the letter chi. I say that because every once in a while you'll hear me slip from electronegativity to chi, a chi value. Okay, so we use it looks like an X, the symbol for electronegativity. Now, electronegativity is pretty cool because it actually, let me put this whole slide up here so you can start filling it in. Okay, it actually looks at a tug of war for electrons between two atoms. So in my mind, when I think of electronegativity, it looks something like this. So we have atom A. Let me pick a different color. I'll pick green. We have atom A and we have atom B, and they're going to have a chemical bond between them. So the question is, with that chemical bond, are electrons going to be transferred or are they going to be shared? So I'm going to go ahead and just draw a dash in there. And B actually has a certain electronegativity. It's a pull towards B, electronegativity of B. And A has a pull towards A, electronegativity of A. It's a tug of war for electrons. I'll go ahead and put, well, one of the things we're going to talk about, let me go ahead and just say a pair or two electrons. I'm going to put two electrons between the A and the B. So it's a tug of war, electronegativity. Now, we already kind of talked about the types of electrons that, or excuse me, not electrons, the types of elements that are just like, dude, I don't want any, I'm okay with giving up an electron. We said that metals are like, dude. So their chi values, electronegativity of metals is very low. The higher the electronegativity, the more it wants to hoard electrons to itself. Generally speaking, metals have low chi or low electronegativity values. So in this unit, we're going to talk about some trends, and oftentimes the trends are limited to just certain elements on the periodic table. So we're going to take the periodic table and we're going to squish the group A elements. So if you remember how that works, we have 1A, 2A, and then we have the B's, and then we have 3A through 8A. So basically our S block and our P block. We're going to squish them together and we have this trend in electronegativities. It increases the closer you get to nonmetals, and that makes sense because nonmetals are like, remember with chlorine, like, yeah, give me the electron, right? And maybe not so intuitive. In the same group, it increases as you get lighter. Okay, so I know I have kind of the arrows going like this, but I kind of think of them kind of coming together. So I think of this one, it increases, and then I think of this one as it increases. So I kind of end up going like that. Okay, so these guys over here are basically the ones that are just pulling for the electrons. Okay, these guys over here, okay, you can have them. All form a positively charged ion, a cation. So I was just thinking about this now. Actually, there are three ways of saying electronegativity. You can say electronegativity, you can say the chi value, or you can say the Pauling value, and I probably say all of them. So Linus Pauling, back, I don't know what year it was, but actually got a Nobel Prize in looking and deciphering, understanding electronegativities of atoms as they're bonded to other atoms. I think that is so cool. So there's this one, and then there's this one. And actually this is the one, I don't know if you guys can read the little numbers in the handouts, but I printed it, I have a copy of it here. So these are the electronegativity values, the chi values, the Pauling values, whatever you want to call them. And again, they increase from left to right, and they increase from the bottom up. Just for the group A elements. So it's kind of like a tug of war. If you have too much of a difference between the atoms that you're connecting together, like we do between sodium and chlorine, basically the one with the higher electronegativity value absconds onto an electron, like we saw in chlorine. Okay, so an electron is transferred. Electron's transferred, the chemical bond is ionic. And there's actually a threshold we're going to say where we can actually do some kind of cool little subtraction problems to kind of look at the two atoms that are joined together, look at their electronegativity values, do a subtraction and kind of see, and we usually do 1.7 as the threshold beyond which electrons are transferred. Small differences in electrons will be shared. So make sure we're all on the same page here. Ionic, E transferred. I can never remember, it's 2 R's, I think it's just 1, but we'll go with 2. And here, electrons shared. Okay. Oh, and let's just go ahead and finish that thought. Up here, we have a metal and a non-metal. And here we have 2 nonmetals. Non-metal, non-metal. Cool. Okay, so usually the difference between the electronegativity values of 2 nonmetals, it'll be less than the 1.7 I'm talking about. There's a slide coming up that has 1.7. So electrons will be shared. And usually if you pick kind of randomly, if you pick any metal, okay, and any non-metal, and you're going to connect them together, you're going to get a difference of more than 1.7. Electrons going to be transferred from the metal to the non-metal, and then you have a dot, dot, dot ionic bond is formed. It's a tug of war, I'm telling you. It's a jungle out there. So it's possible, though, for electrons to be shared, but they're not shared equally because of the tug of war going on. So, for instance, if we look at kind of an assortment of things. So sodium chloride is ionic, electron transferred from the sodium to the chlorine. HCl, I believe, is covalent. And Cl2, one chlorine and another chlorine, guess what their tug of war looks like? They're the same. The electronegative value, their tug of war is 0. The difference, what we say, is 0. So blue is electron deficient, okay, kind of positively charged-ish. Red is electron rich, negatively charged. So yeah, here is the chlorine molecule. Notice that there's the tug of war is kind of, they're tugging, no one's winning, no one's losing, okay? This is actually what we call a polar molecule, where, let's just find it here. Chlorine has an electronegative value of 3.0, hydrogen 2.1. So 3.0 wins over 2.1. So 3.0, that's why that chlorine is a little on the rich side, kind of pinkish over here. Okay. And then the last one, sodium chloride. Okay, sodium very deficient, electron deficient, and chlorine very electron rich. So there's actually, the thing about covalent chemical bonds is there are kind of flavors of where electrons are shared. If they're shared equally, we actually call that nonpolar, okay? If they are shared unequally, like the chlorine and the hydrogen, then we call it, it has a degree of polarity. And this is just kind of looking at them. Okay. So I know earlier in this class, do you remember delta T's? What are delta T's? They're temperature differences. Delta H's, what are they? Enthalpy differences. So delta chi, electronegativity differences. And you guys know what do those lines mean? Absolute value of, yep. Okay. So basically, if you want to know the character of the chemical bond that's connecting atoms, you look at their Pauling value and you subtract them and take the absolute value of that difference. Okay. So the first four listed here, if your delta chi's, your electronegativity differences are even up to 1.2, that tug of war is going on, and the one with the higher electronegative value is going to be partially negative, okay? But electron won't be transferred, it'll be shared. So we call that a strongly polar covalent bond. 1.0, moderately polar. 0.5, weakly polar, and with the Cl2 we saw a minute ago, nonpolar. Okay? A degree of polarity, which actually is a player in how that molecule is going to play with itself and with others.
Well, you said the Cl was nonpolar?
Cl2 was Cl2.
Oh, okay.
When you have two chlorine atoms. You have the HCl was polar. Yeah. So I kind of feel like we're recapping here. Okay. If you have in your form, again, I do this for my intro students. I give them a formula and I say, is that formula represent a molecular compound or an ionic compound? And I tell them, look for the metal. If you have a metal, then you have an ionic compound, most likely. No metals, and basically all you have is electrons being shared all over the place. You have a molecular compound, covalent compound. Here are some electronegativities of your nonmetals that can join together. And this is where I kind of like to look. I'm like, now, if I join this atom with that atom and I figure the difference in electronegativities, do I go past 1.7? And probably not. Okay. So, actually, this is getting back to one of the things that we just talked about when we finished up part 2 earlier. The valence shell electrons. Okay, we said that if you're coming up with how the electrons are configured, those are going to be the ones in their highest N. Collectively, they make the valence shell. So with this whole octet thing, whole electrons being transferred and or shared, it's the valence electrons that are going to do the heavy lifting. I feel like we've already kind of talked about this. We talked about the octet, okay, the whole rare gas configuration, the NS2, NP6, it all means the same thing. Okay, so that gives us just a few minutes to talk about actually the next part. That's wonderful. But notice that there's no homework due. And even the little bit we're going to talk about, I want to go on to the next part. Kind of give you a little precursor for tomorrow. Tomorrow we're focusing only on ionic compounds. Okay? And we're not going to go by that because that's off, but I got 4 minutes. Who's counting? Actually, it might take 4 minutes for this thing to come up. There it goes. So what's that?
Just psyched you out.
It did psych me out. Okay, so this is actually sodium chloride. It's got written all over it. We said that the sodium will lose an electron, become plus, and the chlorine will take up an electron, become negative. Okay. So you see the jag, the black jag there. That jag's better than this jag. Okay, but of course that separates metals from nonmetals. And we're going to see that the reason things like sodium lost 1 electron, the reason it loses just 1 is it gets the rare gas configuration of the element of the rare gas before it. So, for instance, what you see here is sodium is period 3, okay? So when it loses 1 electron, it actually gets the rare gas configuration of the element in period 2, which it's looking like it's neon. So that's why this does that. Sodium goes to form neon. Okay, we all on the same page there. Actually, tomorrow, and this is why I wanted to get you guys to have this, in case you want to start marking up. tomorrow, one of the things we're going to find out is that all of, and you probably already know this, that all of the 1A elements, I'm going to kind of ignore hydrogen for now, actually, like sodium, they form a +1 charge. They lose their 1 valence electron. Okay? Let me pick a different color. All the 2A, starting with beryllium down, they lose their 2 valence electrons and they form a +2 charge. Okay? And then metals only, metals need only apply. So boron is actually on the wrong side of the railroad tracks to be a metal. So starting with aluminum, gallium, and indium, they actually lose their 3 valence electrons to form a +3 charge. So sometimes students like to kind of write that on their periodic table. So there's the JAG again, but now emphasized are the nonmetals, okay? So the nonmetals, like chlorine, pick up electrons. So we said that chlorine specifically is going to pick up 1 electron. Here's chlorine, along with its halogen friends, okay? It's going to pick up 1 electron, and it's going to become a -1 charge. Now the difference between the two is that as it picks up 1 electron, okay, it's actually going to be like the rare gas in its period. So chlorine's going to be like argon, bromine's going to be like krypton, iodine's going to be like xenon. Okay, so sometimes what students like to do is the 7A, they put a -1 because that's how they're all going to behave. The 6A, they put a -2 because that's how they're going to behave, pick up 2 electrons. And then the 5A, they pick up 3 electrons, become a -3 cation.
And
4A, they can sometimes go a little bit either way. So you can't really hang your hat on. The ones I said, the 1A, 2A, 3A, and the 7A, 6A, 5A, you can hang your hat on it. And that's a phrase I use tomorrow. It's just like, you just know what they're going to do. 4A, not so much. Well, that's about how much time we have. So that's a good kind of start into tomorrow's lab.
Since boron's both the zigzag, would it gain 3?
No, but it's a 3A, but it's a non-metal. So I said 3A metals, so beginning with aluminum.
Yeah,
Yeah.
okay. Below plus
Yeah,
above
the metals,
negative.
yeah.
But the same number in the column either way, right?
So boron, you can't hang your hat on it. And you
Oh.
can't hang your hat on carbon or whatever below carbon.
Oh,
Or
okay.
anything here. Yeah.
I think I forgot to do this in
Oh.
my lab.
Okay.
I know it's late, but
That's fine. I can handle that.